And again, what we're going to learn about is how each of the transformations, so it's a bit of a review from the first chapter that we did, how each of those transformations in particular affect the sine, the cosine, and the tangent graph. And for a lot of them, we're going to be focusing mainly on the sine and cosine graphs. So the first thing that we're looking at is this a value. And in the graph, that a value affects the amplitude. So when y equals 2/3 sine x, we have the regular sine x graph here, and the 2/3 sine x, which is a vertical compression. Well, the shortcut is if you draw everything else out, only the amplitude changes. So instead of going up to 1 and down to -1, now it goes up to 2/3 and down to -2/3. So every time we're going to graph sine and cosine, and we'll start here by drawing the regular graph of cosine. Whenever you graph your regular graph of sine and cosine, it has an amplitude of 1, so you can mark your maximum and your minimum. A period of 2 pi, so you can mark your period and divide it into 4 equal sections, which is just your axes family. And we have to remember that the cos graph starts at a maximum. And if it starts at a maximum, then you can go and just jump to the middle, jump to the minimum, back to the middle, back to the maximum. And this is your cos graph. Now we're going to graph right beside this y equals -4 cos x. So we have an a value here, and this a value is a -4. This is going to tell us that our amplitude, and amplitude is always a measurement from the middle to the maximum, your amplitude is always a positive value. So that -4, that means you're going to have in transformation language, you're going to have a vertical reflection and a vertical stretch. And you can write those both at once. You would multiply your y values by -4. Our shortcut for graphing this is we're going to start the same way. But instead of marking a max of 1 and a min of 1, if our amplitude is 4, that means we'll go up to +4 and down to -4. Our period is still 2 pi. That gets divided into 4 equal sections. There's our axes family. And a cos graph normally starts at a maximum. Does it make sense to you that this vertical reflection being flipped over instead of starting at a maximum, that would force it to start at a minimum? And here's how we can draw a cos graph very quickly. Because in transformations, I would have made you take all 5 points and figure out where the new points are. We can do that a lot quicker now, just saying, hey, if I know it starts at a minimum, and I use my amplitude to find my minimum, then I'm going to go from minimum to middle to maximum to middle to minimum. And you can draw your graph very, very quickly. Okay? Some common mistakes, right? It's a rounded graph. If you draw straight lines like this, they will take off a half a mark that your shape is off. So a rounded curve through those. And if we know where it starts, for cos graph normally starts at a maximum. The reflection would make it start at a minimum. A sine graph starts in the middle, going up. A negative sine graph would start in the middle, going down. And our a value gives us our amplitude, which is a shortcut to find where our maximum and our minimum are. So that's the first thing we look at. Today, we start with example 2. Well, after that little review of example 1. And we're going to look at what in particular the B value, your horizontal stretches and compressions, what do they affect? So again, in A, we have y equals cos x, cos 6x, and this 6, the B value in transformation language, would be a horizontal compression. You would multiply your x values by 1/6. Does it make sense that that's going to affect your period? Because your period was 2 pi, and now you're compressing it by 1/6. Does it make sense that your new period, if your period was 2 pi, and you're compressing it by 1/6, your new period will be 2 pi over 6. So again, in our heads, we have our regular cos graph here. I'll draw it quickly. 1 and minus 1. Period of 2 pi divided into 4 equal sections. Here's our regular cos graph, starting at maximum, then middle, then min, then middle, then max. Here's our regular cos graph. What's going to happen? Well, when we go to graph it, we already know our amplitude stayed the same, so it's still going to have 1 and minus 1. But now our period is 2 pi over 6. So on my axes, I'm going to make a mark. And that reduces to pi over 3. And instead of starting by marking 2 pi, I'm starting by marking pi over 3. Because that's my new period. And I divide that into 4 equal sections. So a little bit of mental math to do here. How do you label those 4 equal sections if the pi over 3 is there on the right? Okay. For me personally, I think it's easiest to label the one in the middle first. Would you agree that the one in the middle has to be half of this one? And if you multiply that by a half, that would multiply your denominator by 2. That would give you pi over 6. So I find that one's the easiest one to label first, because it's half of the pi over 3. And then the next one would be the first one. Because if this was half of pi over 3, does it make sense that the first one would be half of pi over 6? And so if I multiply the pi over 6 by half, I will get pi over 12. And if I know that each of these sections are equally spaced, and the first one is pi over 12, technically I could think of the second one as 2 pi over 12s, because it's 2 of them. And the third one as 3 pi over 12s. And I don't mind if you write it like that, or you reduce it to pi over 4. But that's the way I'd like you to think about labeling these. Label your period first. Split it into 4 equal sections. Find the middle one, because it's half of pi over 3. Then find the first one, because it's half of pi over 6. Then find the third one just by counting. Well, if the first one's 1 pi over 12, 2 pi over 12, 3 pi over 12s, you can label the third one. And now that you've got your period labeled with 4 equal sections, this is a cos graph. A cos graph starts at a maximum. So I go to my maximum, then my first ticking mark is the center line, then minimum, then middle, then maximum. And instead of having to do transformations with all 5 of those points, this will be a little bit quicker to graph. And we notice that the B value, whereas the A value changed your amplitude, your B value changes your period. And the letter P and the letter B are very close, so I think they sound period. You can almost period, oh, maybe. I don't know. I don't know if that's going to help you remember. But your B value affects your period. Actually, I'll do C first, because sine and cosine are very similar. So we'll do y equals sine x over 7 first, which is the same as y equals sine of 1/7. So if we did transformations, this would be a horizontal stretch. You would multiply your x values, because x's are liars, by the reciprocal, by 7/1. So you'd multiply your x values by 7. And again, I'll draw a quick regular graph of sine. Your axes family. Sine starts in the middle going up, so first kick you mark maximum, then middle, then minimum, then middle. This is our regular sine graph. Can you see that a horizontal stretch or compression is going to change that period? That was 2 pi. It's going to get stretched way out. Can you see that your new period, if you multiply by 7, would be 14 pi? Because you're stretching it out by a factor of 7. So if it was 2 pi, this point right here at 2 pi, if you multiplied that by 7, would go to 14 pi. So the shortcut for graphing sine of x over 7, you'd see your amplitude is still 1, so you'd go up to 1 and minus 1. And now your period is 14 pi, so I pick some random place on my x-axis and label 14 pi. Then I have to divide this into 4 equal sections. Cut it in half and then cut each of those in half. The easiest one to label will be the one in the middle. What's half of 14?
7.
That'll be 7. What's half of 7?
3.5.
3.5, or you could leave it as a fraction. 7/2. 7 pi over 2. Then the third one. If this is 1 7 pi over 2s, this is 2 7 pi over 2s, this would be 3 7 pi over 2s. 3 7 pi over 2s, well, 3 times 7 would be 21 pi over 2s. And then we have a sine graph. Sine graph starts in the middle, going up, so we start in the middle, then we go to maximum, then to middle, then to minimum, then back to middle. And finally, we'll do B last. B is y equals tan of 2/3 x. The reason I wanted to do B back last is because tan is a little bit different. Okay, here we go. This is going to be a horizontal stretch. You would multiply x by the reciprocal 3/2. And we call it a stretch because 3/2 is 1.5, which is bigger than 1. What does our regular tan graph look like? When graphing your regular tan graph, it makes sense to draw your asymptotes first. So you're going to have, and I'll go a little bit in the negative direction as well. So you have an asymptote at pi over 2 and 3 pi over 2. So notice I'm labeling my axes family. And wherever on your unit circle, you know how at the top and the bottom tan was undefined. Where tangent is undefined on the graph, those show up as vertical asymptotes. Then tan of 0 is 0, tan of pi is 0. Your other axes family, tan is always negative. So at those points, our tan graph looks very similar to an x cubed, a little bit different, because it repeats itself and the curve is slightly different. If you were here we have our tan graph. strategy for graphing your tan graphs that's really helpful is if you start with your asymptotes. So if I start with my asymptotes, on my new one, I'm going to multiply all my x values by 3 over 2. What's going to happen when I multiply pi over 2 times 3 pi over 2? I'm just going to make a mark there. Pi over 2 times 3 pi over 2 will become 3 pi over 4. Same thing. Negative pi over 2 multiplied by 3 over 2 will become negative 3 pi over 4. Those will be new asymptotes. In fact, I could label one more. Right? If I took 3 pi over 2 and I multiplied it by 3 over 2, do you see that you would get 9 pi over 4? So I'll label one more. Then right in between them, and that's all you need to do for your tan graph. Technically on the exam, they might want you to label, like we have nothing labeled on our y-axis. That usually results in an E9 error because we have no scale on our y-axis. Sometimes what you can do to provide scale is just like put a 1 there. Okay? They might accept that for full marks on a tan graph. If you really wanted to be particular on this graph, you know, right, here's 1. I know that tan of pi over 4 is 1. So now on this graph, at 1, what is it going to be? Well, I multiply that pi over 4 times 3 over 2, so it becomes 3 pi over 8, comma 1. And that's how we can label a point on your tangent graph. At the bottom of your page, we're going to add some notes at the bottom of the page, and then I'll give you which questions to work on for this one. So at the bottom of the page, they have the period of a trigonometric function. These are very helpful formulas. In fact, you're going to use this first one for sine and cos a ton. Since the b value is a horizontal stretch or compression, and you do the opposite, you multiply by the reciprocal, which is the same as dividing. If the period was 2 pi, your new period will always be 2 pi divided by your b value. Right? Because if there was a 3 for b, it'd be a horizontal compression by 1/3. That would make your period, which was 2 pi, be multiplied by 1/3, which is like dividing by b. Sometimes we'll know our b value and have to find our period. Sometimes we'll know the graph. You'll be able to see the period and have to draw the equation or write the equation. So we can rearrange this formula, and our b value is always 2 pi over the period. These two formulas are not on your formula sheet. So you'll need to just know this, but it's just based on horizontal stretches and compressions. For tan, the period is different. Sine and cosine, those graphs had a period of 2 pi. Tangent has a period of pi. So its formula is pi over b, or its b value is pi over its period. So I'll get you to circle question 3, C, and D.